All right, welcome back. We are Game 3001. That's Artificial Intelligence for Games in the winter 2022 semester at George Brown, and it's week 11, part one of our broadcast and recording together. And so we're going to be talking about a bunch of different things today, but mostly it's around behavior trees, which is something that is kind of a follow-up from what we talked about last week. Let's review what we did. So last week we talked about state machines. In our lecture, in our lab, we created some path nodes, and each path node had a line of sight capability as well as obstacles. And for path nodes, what we ended up doing was each path node is not really connected. That's not what we did. They were just kind of path nodes that were kind of placed on the screen. We created obstacles, and the obstacles, Alex added some new capabilities for obstacles to give them a buffer of path nodes around them. So that way it would be easy for us to traverse the game world from one path node to the next. That's what we kind of did for you guys last week. And we did this in preparation for what you're going to do for this Sunday, which is when your assignment 3 is due. So that's what's happening. This week we're talking about behavior trees. We're introducing a new lab, Lab 7, which has two parts, Part 1 and 2, which are both due next Sunday, not this Sunday, but next Sunday at midnight. And this corresponds nicely with your assignment 3, which is due this Sunday at midnight. Okay, again, if you haven't signed up for groups of 3, please do so as soon as possible, else you will not be able to submit your assignment 3. And on that, what I wanted to do before I moved on was talk very briefly about assignment 3, and I think this is kind of where you might have some questions that we can possibly answer together. Let's see how this works. I have a question coming in from Jack. Should we use Lab 6 as a base for assignment 3? I think it's a pretty good one to start with, for sure. And the reason for that is because there's a lot of stuff we've already done together, Jack, for assignment 3. So I think it makes sense. You know, that's what I'm thinking. Let's get into that one. Let's go to assignment 3. And I just wanted to take a look at it with you one more time. And because, you know, I know that some people have are still confused about what to do and how to start and all that kind of stuff. And I think it's important to, you know, to discuss it. So again, one more time, assignment 3 due this Sunday, March 27th by midnight. We have some mandatory pieces. We know the start scene. I'm going to skip that part and go right into the play scene. So you must include a node class. Well, we've kind of given you a node class. It's a path node class, so this is pretty good. Sorry, I'm just getting another question here. David says, quick question, Lab 6 window submission isn't available today. Is there still a chance to submit with penalty? Labs are submitted with, when they're due, David. So there's no extension for labs whatsoever, right? So that means when they're due on Sunday, then they're due on Sunday. So maybe you want to see me after, talk about it after, and talk about what happened, okay? All right, so yeah, so let's continue with this one. So again, the play scene, again, we'll just demonstrate decision making. You're going to make a node class. You must create a collection of node pointers. We did that to enable iteration across all nodes. And this could be a STL list. We did this already. This is a grid of nodes. That's what we kind of made for you. And we ensure we select an appropriate actor sprite. Please do not use our spaceship. Okay, when we actually to get you guys to create a the stuff that we've asked you to make, right? What we say is, we want you to create stuff. This is your assignment. The stuff that we've added in or shared with you is for demo purposes. Your job is to make it so that your interesting scene is interesting for us too, right? So this part right here. Just to highlight this, your actor sprite should be your own actor sprite. Please do not use the NCL that we provide for you or the target by any means. This does not make sense for what you're doing. All right, so this is the thing. Because the next part, which we go into, let's just scroll to the next piece, right? So the next part is create an interesting map, right, that is overlaid on top of the nodes. So this is where the nodes, remember, the nodes are only visible in debug mode. And so what you'd be doing is you'd be making an interesting map. And again, there's always questions about what is an interesting map. But basically what you're doing is you can use any way of doing this. You can use a background image if you really want to. And then on top of that, you can overlay a bunch of things like mountains and walls and debris and whatever you want to do, right, as you're traversing. And this can be a bit creative because that gives you some flexibility. And some areas are going to be impassable. So in other words, there are obstacles, right? And again, you may use a tile map set or simply draw your map tiles individually. It's totally up to you how you make this, but it needs to be interesting. Please do not make it so that it's boring and it's a white screen. That would be loss of marks. Okay, so that's the idea behind that one. Okay. The next part is your playseat must include appropriate background music and sound effects. Please do not forget these as they are worth marks as well. All right, so that is something that you should do. Let's talk about your requirements. Can we use the character? What character, Aiden, that you're talking about? You mean the character we've supplied you? No, make your own. Get your own, right? So if you made one for assignment 2, you can certainly use the same character for assignment 2, or even the same tile assets that you use for assignment 2. But please do not use stuff we've supplied you. They're just for labs. All right, so requirements. Let's take a look at this. Okay, so this stuff is going to be reused in assignment 4. A debug view, which we already have. Debug keys, you can use IMGUI. It's not necessary for you to use additionals. But let's suppose you want to show them. You can certainly do that. As an example, the debug view should allow you to get there. And it says will display line of sight raise. This is something that will happen in debug when you go into IMGUI. And a detection radius. We haven't covered a detection radius, but guys, how would you do a detection radius? What would you do there? How would you do the detection radius? Anybody? So how would you display the detection radius, and what would that work like? Any ideas? Guys, for the people that are here. What is a radius? Well, we know that it's part of a circle, right? So what you could do is you could make a circle, draw a circle that basically hovers around, yes, you could do that, Simon, absolutely. Hovers around or is kind of parented to your character. And the character would be an autonomous to the enemy. That's what's going to happen, right? So that's what is going to show up. The enemy is going to have a detection radius. That's how it's going to work, right? Okay, player animations and sound effects. This will trigger various animations and sound effects for the player. An idle animation with no input is triggered, movements, and so on. These animations and all these things are up to you to create. You didn't have to wait till today to get them done. You could have done this anytime, like I mentioned earlier, because they have nothing to do with the actual the demo. You're making a little mini game. And like I showed you when I showed you guys Herman's example from last year, it had the character has their little animations for different things like movement and attacking and a bunch of other stuff. Player capabilities. So this has nothing to do again with the AI, but rather your player, the things that you're controlling. So some kind of close combat and ranged combat attacks. They should be able to do both of those two things. Again, this has nothing to do with the game AI. This is to do with your player setup so that when you move into your second assignment related to this one, which is assignment 4, right, then you will have the ability to move around the screen. Player health bar, you will have to make that as well. These two things, does anyone have trouble making these two things now? Right, if you do, right, again, you need to be able to get them done as soon as possible because they are a requirement for a successful assignment. So these two things, again, if I'm looking at this has nothing to do with the with AI, and neither does this one. Okay, so these three things, this is just dressing to make your game or your application look good. So player combat abilities, right? How do you fight? The health bar and your game status, right? I mean, again, it is something that is required for the assignment, but it has nothing to do with your AI, okay? Not really. So you could have done this anytime. Okay, next. And hopefully you guys have had this already. You have had time to do this because it's important. And that you've learned in fundamentals. Any kind of fundamental stuff that you learned, you can use it to create a health bar. I'm sure that a health bar was covered in fundamentals, and I think it's important for you to be able to do. And a game status is another type of bar. It's a progress bar. You could also use a score label or other thing that will display how many enemies are still active in the scene and how many have been eliminated. You need to be able to keep track of that as to as this is the setup for the next assignment, which is assignment 4, right? All right, play scene will include at least 4 obstacles. Okay, we've given you the ability to put obstacles in place and size them appropriately. So you got to consider that the obstacles we've shown you that are displayed can be your own obstacles, but instead of making them blocks, you would have to make them something that is relatable to your particular level, which means if you used our obstacles, that would not be sufficient. Our obstacles are just placeholders for your own. Certainly your obstacles can be rectangular, right? For example, if you made some kind of, think about your obstacles that we've given you as the colliders, right? The collider boundaries for something that you're actually going to physically show. Okay, so that's what you can do. So when you create your obstacle boundaries, those are the things that are going to stop the path nodes from having line of sight with your player and with the enemy. That's the idea behind that. Okay. So that's what the obstacles are there. They're there to help you. Okay, that's what they're there for you to have. Obstacles will also block enemy line of sight. However, they will not block enemy detection radius. Why? Because these obstacles are the way they work is that they are going to be set in the world, and then your radius, your detection radius, is something that follows the enemies around. Each enemy will have a detection radius, and basically it's just going to hunt for the player. It's going to ignore obstacles. So it's not going to, overlap with obstacles in any way. We don't really care about that. And it says you need 4 of them. So please make sure you have 4. I've seen in the past people have given me 1 obstacle or 2 obstacles. This is not 4 obstacles. You need to give me 4 obstacles. Right? And 4 is really minimal. Also, please don't make your obstacles super small. They will not be obstacles. All right? They have to be something reasonably sized. Why? Otherwise, it won't block line of sight, and you won't be able to demonstrate this during your video, which doesn't make any sense. So I recommend making obstacles fairly decently sized relative to your scene. Okay? So that's something that you should think about. Your base enemy setup, this is your enemy class, okay, that you're kind of putting together. That's why we just called it the base enemy class, because you're going to extend this for assignment number 4. Okay, so that's what you're doing. And they'll be able to move, patrol along a predetermined path. So predetermined path means you will give it a path and it will just keep moving around it. That's all it's going to do right now. Okay. The base enemy game object will have a health property, which will be displayed in a health bar. Well, if you're doing a health bar for your player, then you can use the same kind of health bar class or the health bar itself. Again, this has nothing to do with AI, but we need it for status, right? And you're going to put that same kind of health bar next to the enemy, above the enemy's head, whatever you're going to do it, so that we can see what the enemy's health is. Each enemy will require a bar. Please do not make them fixed on the screen, let's say at different corners. They will have to follow the enemy, okay? However, the player's health bar, some people make the player's health bar at the top of the screen. That is acceptable, right? But the base enemy health bar will have to move with them. Yes, Aiden, that's why there's so much to do here, and that's why it doesn't make sense for you to do it the last minute this last week. Base enemy will also have animations and sound effects. This has nothing to do with AI. You could have done this at any time. So please get going on this with you and your partner, because, again, at the end of the day, this has literally 0 to do with AI. Okay, it has to do with fundamentals, making your enemy have animations and sound effects. Okay, base enemy line of sight. Okay, this is interesting. So we've given line of sight to your player in the game. Okay, in the lab that we've given you. Well, you need to give your enemy line of sight. Okay, so the enemy must have line of sight now instead of the player. Okay, so this is not a great departure for what we've already given you. And what does this mean? That means they will calculate to keep track of whether or not they have line of sight with the player. You will need to account for any obstacles that may block line of sight in the calculation. So, simple way of doing this is, if the player is visible anywhere on the map, right, then the enemy has line of sight, right? In other words, if they're on a node, a path node, this is the way I would probably do this to solve this problem. If the enemy is on a path node that has line of sight with the player, then the enemy has line of sight. Make sense? So let me say that again. If the enemy is on a path node that has line of sight with the player, then the enemy too has line of sight. Okay, you don't have to have a line of sight distance for the enemy. The enemy can see anywhere on the screen, right? As an example, as long as they're not being blocked by some kind of obstacle, they will see the player. That's why you need to make obstacles fairly large size. Okay, enemy detection radius is important. A simple algorithm that determines the player is within each enemy's detection radius, which can be a range of your choosing. Like the line of sight check, it can be stored as a Boolean and will be used for the next assignment. Okay, so is the player in the enemy's detection radius? Remember, those are the two things that are part of the enemy's sensing suite. This is the two things here, all right? So this is critical for you to have these in place before next assignment. Critical, okay? And that's it. It does not tell you that the enemy has to kill the player, do anything with the player, or whatever. This is all setup, a foundation, for everything that you're doing for assignment 4. Really, at the end of the day, the most difficult part we've already solved for you because of the enemy line of sight thing, okay? Because we already have this in place. The path nodes give you this capability. If the enemy is on a path node, as an example, that has line of sight, so it has line of sight too, right? You can make sure that that is clear, right? And the enemies, when it comes to traversing the game world, right? When we think about this, remember what we say up here is the enemy capabilities is the ability for the enemy to, patrol around the world. That's what happens with this thing. So that is something that you want to talk about when it comes to the enemy base class. I'm just searching here for anything else that you might need. So again, think about this enemy base class worth 10 marks, 10% of your grade for this assignment, right? They will be able to move, patrol along a predetermined path of nodes. That means they will be part or on a node at some point or another, right? Now we've given you 300 nodes that are inside of your map. Do you have to use, here's a question for you. Do you have to use our path node class? Probably is a good idea, but do you have to? No, you can make your own if you really want to. I don't recommend it, right? Since we've already given you it, might as well use what we've given you. And the second thing is, what about if you wanted to make it more dense? More nodes. Is that something that you could do? We've given you 300, right? Because we've given you a scene of 25 by 15, if I'm not wrong, or is it 20 by 15? 20 by 15 path nodes, which is equivalent to what we did with the tiles. Can you make this denser? Yes, you could. You can make it so that you have, double that amount if you really want to. It doesn't really matter, right? Because at the end of the day, it's just going to give more accurate movement if you so need it, right? But it's probably good enough. The things we've given you for our grid of nodes and all that stuff is probably good enough for what you're doing. But what this means is when you're patrolling, and let's suppose you're patrolling around the screen, that will be a very easy way to do it. You have to kind of figure out, how do you move your enemy now? How are you moving your enemy around the screen, right? If I'm patrolling, what does that patrol mean for you, right? So again, you're moving from one path node to the other. Remember that the enemy cannot move through obstacles, so don't patrol an enemy right through an obstacle. You're making this predetermined path. I'm not showing you what this is. This is your path, whatever you decide to make it, right? But again, guys, what I would like you to do, right, when it comes to your enemy, right, is, it's for demo purposes. Make sure that the enemy can, when you're in debug mode and the player is within line of sight, the enemy can see them. One thing to do is for you, draw a line between the enemy and the player. And you could do that as well, instead of just using the path nodes. It's really up to you how you implement this thing. But I recommend, you would work with this to make sure that, that it is correct. It says, when the enemy game object is hit, now this is something you need to respond to, right? So the enemy can't hit, right? The enemy can't hit right now, not really. But the player can hit the enemy. They can fire at the enemy because the player has capabilities of fighting. Remember we said that. Player combat capabilities. It can fire and forget. It can do a melee combat attack with animations. All those kind of things. But the enemy does not have that right now. The enemy can only walk around, really. The only way that the player can be damaged, and I recommend you do this as well, is if the enemy collides with the player. That would be the only way that the player can be damaged at this point. Because at the end of the day, when we think about this, we haven't said how many enemies. We've only said make an enemy. Right, one enemy right now that patrols around, and there's one player. Okay, so I'm just trying to point this out for you and clarify, because I've had a number of emails that have come my way and I've said things like, so how many players do I need? 1. How many enemies do I need? Well, minimum 1 is what you need to test this out. And that 1 enemy should probably patrol. However, I want to also mention that there's another assignment coming up, right? So it makes sense, like we said, that's why we've given you these 2 assignments, to plan for both of them, okay? Let's take a look and see what assignment 4 requires if you're doing it, so you don't have to do a lot of rework, okay? Again, up to 3 members for both of these assignments. It's very important to understand that. Try not to do this assignment completely on your own, as it is very difficult because there's a lot of details. Not because it's difficult you can't do it. It's difficult because there's a lot of stuff to do, okay? Your AI, which is your enemy, will now have a bunch of actions that it can perform, okay? That's what it says here. So this is what you're going to be doing, right? So, and you're going to have at least 2 loadouts, right? That means there's going to be at least 2 enemies right now, because remember what we're saying is we have 2 enemies, a close combat enemy, right? And a ranged combat enemy, 2 different kinds of enemies. Both are able to patrol. Take a look. Their patrol action is something that they're going to have, right? That is the patrol action. That means that you should probably solidify what that patrol action means for each enemy. And that probably means, if I was you, knowing that assignment 4 was coming, which we do, then it makes sense for you to make 2 enemies, right? 1 enemy that patrols in one way and another enemy that patrols another way, right? So that way when you shift to assignment 4, you already have these 2 enemies in place with their proper patrol route. So you don't have to do that again for assignment 4. Get 2 of them done, right? That's what I recommend. Now, do you have to? No. Should you? Probably. That's what I recommend you do. Okay, Destructible Environment. You know this is coming, right? It's coming, right? Where, you know, obstacles in your assignment 4 it's coming up. So it says a subclass of the obstacle class. This is the thing with that is going to be a destructible obstacle, right? So that's what's happening there with this one. Okay, so make half of the obstacles in the scene destructible, right? That is half of the ones you already have. That means out of 4 obstacles, if you only went with 4, by the way, you can have more than 4. We've asked you to put 4, at least 4, in assignment 3, right? So if you look at assignment 3, it says you must have 4 obstacles. That's what we said here, right? There must be 4 obstacles in the scene, okay? But doesn't mean that you only need to have 4. You can have 8. You can have 10 if they make sense. If it's like something that makes sense for the scene. You're making this. This is your kind of mini game that you're creating, right? So that means in assignment 4, half of them should be destructible. The other half may not be. It's up to you which ones are not destructible. Enemy respawning? Well, if you're going to do respawning, you might as well do spawning for assignment 3, right? How do the enemy spawn? They get instantiated and they get added to the scene. Should they start on the scene, in the scene, or should they enter the scene? What do you recommend that they do? Remember Herman's game example, right? Where the enemies came onto the scene after the player was added. The player was added first, and then the enemies came onto the scene, right? This might be something you want to consider. Some kind of winning condition is coming up, right? And that is what's happening. So it's kind of a very simple game, but at the end of the day, you know, you should consider that the second assignment related to this one is more difficult than this one is. This is literally just make your enemy patrol around the scene. That's what it's going to do. Okay? So notice that in obstacles, we say at least 4 obstacles to stop the player and enemies from passing around, right? So we never told you how many enemies. We never said we want you to have 2 enemies, 1 enemy, 3 enemies. We never said that. I'm telling you, you have to have at least 1. I recommend at least 2, so that way you're ready to go for assignment 4. This is where the mark breakdown comes from. Your start scene, your place scene, debug views and keys. This is important because things that you can do in your UI, it doesn't matter whether you're using keys or not, right? If you're using IMGUI, and you can use IMGUI properly, we put the debug keys in there just in case you have trouble using IMGUI, which has really nothing to do with your AI. That's why it's here like this, right? But you can certainly use IMGUI instead of debug keys, like keyboard shortcuts, although I recommend both. There's nothing wrong with adding both the keys and IMGUI stuff to make sense of the same thing, right? Because I think quick shortcut keys are great ways of demonstrating what you're doing without going into IMGUI. All right, so that's something you can do. But you should be able to display when you're demonstrating your application, which is really what you're doing, your little game app, right? What you should try and do is demo all the parts that we've asked you about, right? So hey, here is my my character. Look, here's the attack animation. Look, here's the ranged attack animation. Hey, look, here is them. The enemy is detecting the player in their detection radius. Oh, here the enemy is detecting the player by using line of sight. Demonstrate the things we've asked you to do. Make it easier for us to give you full marks, guys. Okay, as an example. Okay, so that's player criteria. As an example, here's the player criteria, how it works. And the base enemy criteria is right here, as well as source control and the submission requirements. Okay, any questions around assignment 3? And since we talked about assignment 4, any questions around assignment 4? But assignment 3 is due this Sunday. So if you've been waiting around to get this started, well, there's a lot of work for you to do. It's not impossible, but there's a lot of work for you to do between now and Sunday. Okay? Questions, please. Please, please. I'm asking you for questions. I can answer your questions now before we move on to other topics. No questions. Okay. You can always put up your hand too if you want to talk. Yes, Lucas. I'm here to answer your questions live. Let's try and do it together. Hanson asks, do we have to do all the things to get full marks or just mandatory? You need to do all the things to get full marks. You need to do the mandatory things or you won't get any marks, right? So Jack says, so we need a character with 2 different attack animations. Yes. 1 attack animation for remote, like a, some kind of ranged attack, and a melee attack. Aiden says, so pretty much all answers we need are in classes like labs. Yeah, for the most part, Aiden. What we get together is when Alex and I do the labs with you guys, they're there to help you, right? We're trying to get you closer to doing your assignments. That's what it is. It's not, again, it's not to be oppressive. We're not trying to do that. We're saying, okay, here's a framework. This is the challenge. That your challenge or your evaluation is are the assignments that we give you. Ethan says, do we have to be able to switch between weapons for melee and ranged, or can they just be binded to 2 different buttons? They can be bound to 2 different buttons for sure. You can just use, so let's say, for example, you want to attack with your mouse. You can listen to your mouse attacks. Left mouse button does the, kind of melee attack. Right mouse button does a ranged attack. It's totally up to you. Or you can use keyboard as well, right? Lucas says, current group that I'm in said that they have the members they want and want me to leave their group. Okay. I can do that for sure, Lucas. I'm just going to take care of that requirement offline. So what I need from you for that one, I'm going to come back to this one. For what I need from you is your group number, please, for 38. Thank you. 1 second, and we'll just take care of that right away. Anyone else have any group issues? And that's group 38 for A3 groups, if I'm not wrong, right? So that's something that you need to have as well. A3 groups. Just a moment. And what about A4 groups? Are you also in the wrong group, Lucas, for A4 groups or just for A3 groups? You've been removed. Are you in the same group for A4 groups? Remember, there's 2 groups, A3 group and A4 group. Aiden says, do I need to join a group if I'm by myself? Yes. You need to have a group of 1 minimum if you're doing it by yourself. I also have a thing from David saying still looking for a group. Okay, David, no problem. Worst case scenario, join a group of 1. That would be very bad at this point since we're sitting at, again, week 10 and this is when it's due, but, It is what it is. I understand it's difficult to combine with. There we go. So Aiden, are you part of a group yet? Or David, are you part of a group yet? Okay, if you're not, please let me know and I will switch those out right now. So we'll get you guys going. Otherwise, you can join an empty group and you're good to go. All right. So that's the only questions I had was about the assignment was groups, really, and whether or not, that you need to get full marks and so on. So any other questions around the tech required for the assignment? If you have a question about how to do something, this might be something that you might go for. For example, you might have questions about, as an example, how to do something that's in here. If you do, this is a good time to ask because I'm going to move on to other topics now. All right. If you think about anything before the end of our time together today, then please let me know and I will try and answer your questions. I'd like to try and keep it as a forum, as opposed to something that is individually sent to me, because this week we can answer everyone's question that might have the same kind of question as opposed to just one person. Tarif says, for the melee attack, is it only if the enemy is in front of the player? Well, you can perform a melee attack and miss. So the answer is you should be able to do the melee attack animation and attempt to attack. But the only time it's going to work and damage the enemy is if the player and the enemy are fairly close. Yes, you can do that, Jack. So Jack's asking for a group naming. Yeah, you can just put last names like we asked you to. Yeah. With maybe, again, it can be very long. If it's too long, as an example, you might want to, especially if the last names are very long, it might be something you want to think about. As long as it makes sense that it's, each of your names are part of that, the people that are in there is fine. You also have to demonstrate it anyway. So something that is, the naming should be something related to the last names. How about that? Worst case, first 3 characters or something. Okay. So again, anyone else have any other questions related to this topic, which is assignment 3, before we move on? David says, is there a Discord channel or would you like me to create one? No, sorry, that's not related to me. All right, guys, we're going to move on then. Sounds like, we are, if you guys have questions, you might have some later for this one. I'm going to move into what we're talking about today. So again, we're sitting here at week 11. And so far we've covered decision trees, state machines, and now behavior trees. And one thing we were talking about with myself and Alex was, can we not, would it be interesting for you guys to, to kind of construct a diagram of the same things we've asked you to do with the 3 types of decision-making algorithms or structures. Sorry, these are data structures that we've given you. So decision trees is a kind of data structure and an algorithm, state machines another type. And now the third one, which is behavior trees, they all kind of do very similar things, but we're going to talk about what one does compared to the other. All right, so that's what we're talking about today in today's lecture. So let's think about what's going to happen in the future. So next week, again, we're finishing off Lab 7. And notice that this week at the end, we're going to have you build a tree node class because we're going to try and get you to construct a decision tree. All right, that's where we're focusing on for assignment 3 and 4, a decision tree. So you're building a tree node class this week and conditions and actions. And then next week, we're talking about goal-oriented behavior and rule-based systems. So we're moving away from our patterns. But in week 12, we're also asking you to construct different actions to help you with your assignment 4, right? So that's what's happening here. Notice that we're saying move to player action, move to line of sight action, move to range action. We're going to help you build these things. We're also going to revisit seek and arrival, because what we're hoping that you're going to do is, okay, when the player is moving towards our, when the enemy is moving towards the player, they need to use some kind of steering behaviors in order for them to move towards the player, and seeking and arrival are the 2, behaviors that might make sense, along with, look where you're going. That's something that you're probably going to have to do to make your game look good for this assignment, right? Assignment 4. And after that, we're getting into utility theory, where we're revisiting. It looks like lab 7. I think we made it a 3-parter. So what we're going to probably do is, I didn't notice that. I'm just going to switch that up now. So sorry about that. That is not what I expected. And the reason for this, by the way, guys, is Alex and I have switched out some stuff. So this is actually due, lab 7 is, part 3 is due week 13, right? So that is when it's due, not week 12. So that's a mistake. I'm just going to correct that right now, just so that way there's no issues. So it's going to be Sunday, April the 10th is when this is due, not Sunday, April the 3rd. So that's when it's going to be due, and it's going to be worth 12% of your final grade, right? Because each lab is worth 4%. Okay, this is 12. Okay, and I've kind of put that together for you up there. So that's when it's due. So lab 7 then is going to be finished week 13. Let me just update that as well in here. 1, 2, and 3, right? Which is going to be due week 13. Okay, just to give you a change up online, just a bit of administration change. So yeah, so that is when lab 7 is due, and notice that we're helping you build all the actions, right, for assignment 4 for the most part, up until about lab 7. Okay, so that's what's happening here. Lab 8, which starts on week 14, is something else, but we're also going to be showing you, it's kind of still continuing from lab 7, right, as an example, and it's aligned with assignment 4, right, which is due around the same week. Assignment 5, remember, is just a presentation, is what you're doing for assignment 5 that you're going to be presenting during the last week of class. Okay, so we'll be talking about that. So during labs, right, there will be no labs for the last week of class, but rather assignment 4 presentations, right, that we're going to be doing there for that last week, right? So please make sure that's you're going to be ready for that. And we're going to give you more details around assignment 5 around week 14, when we're going to put that together for you. Okay, so that's what's happening in terms of our administration. And moving on. So this week we've been talking about, last week we talked about hierarchical state machines and state machines in general. And this week we're going to continue that topic as an example with, the stuff we're talking about with behavior trees. So instead of a state with behavior trees, because we talked about states last week, the main building blocks of a behavior tree is a task. So you have several tasks that you're going to have. And then tasks are composed into subtrees for more complex actions. But I want to mention something in terms of the way it works. They have 3 types of tasks that we're going to be looking for behavior trees. Conditions, so something that tests a test of some kind, right? An action, something that you're going to be doing. And there's going to be some composites. And composite tasks are either a selector or a sequence. So those are the basic ones that we're going to look at, okay? So behavior trees are kind of like, they're still in a tree-like structure, but they're not necessarily binary trees. Just like decision trees, for the most part, are mostly binary trees. Okay, that's what makes them really quick and easy and all that kind of stuff. But behavior trees are not. Composite tasks, let's talk about that a little bit. So they are going to run their own child behaviors in each of the composite tasks. So one of them, the selector, it returns immediately with either a success status code or a failure status code. One of those 2 things, okay? So it returns with a success status code when one of its children runs successfully, okay? A sequence returns immediately with a failure status code when one of its children fails. So that's what's going to happen there, okay? So that's the difference between a selector and a sequence. We'll talk about this in a second, okay? Here's an example of a selector. So a selector has a circle. That's the kind of the way it looks. Let's kind of focus in here on this, just on this one part, right? So a selector then will have a some children, right? And the children from a selector, you're going to select one of these attacks, and it's going to return success when one of these three things, is successful, whether it's an attack that's successful or a taunt or a stare. In this particular case, one of these three things, if you can accomplish these three actions, one of them, it's going to return true or successful. Okay. What about a sequence? A sequence, it's denoted by this rectangle with an arrow. What happens is we start with the leftmost child in the sequence. So for example, is the enemy visible? No. Returns no here. Okay, let's go to the next one. If it's then turn away, right? If the enemy is not visible, then turn away, right? Or think about this. If it comes back as no, the whole thing fails, right? If any one of these things fail, then the whole thing fails. So how about this? Is the enemy visible? Yes. Turn away. Okay, we're able to turn away? Yes. Cool. Run away. If I can do these three things, that's the sequence. We start here, then we go there, and then we go there. But anytime one of these three things fails, then the whole node fails. That's how it works. Okay. So, and that's the difference between a selector and a sequence. Sequence, any of these things is true, then the whole node becomes true. Whereas any one of these things is false, then the whole node becomes false, or fail, if you will. So success or failure. What we can do with this, of course, is combine them. And the simplest behavior tree would be something that looks like this. Move into room. So no child nodes, just an action. That's the simplest behavior tree. So we think about a behavior tree, you could combine them. So here's a composition of nodes, right? And so let's suppose I have a selector. A selector says any one of these two sequences can be true for the whole thing to be true. Okay, so let's try this out. So any one of these two. So let's see this one. So is the door open? No. That is false. So that goes up to here, and then we try this one. Okay, how about this one? Can we move to the door? Yes. Cool. Can I open the door? Let's say yes. And then move into the room. Yes, right? If the door wasn't open, then we'd want to do this one. Does that make sense? Because you can't do both. It's either one or the other. That's why it's called the selector. The first node that returns true, the first child node that returns true is the one that we're actually going to finish performing. All right. So here, if this is false, let's say for this is false, then what's going to happen is, because this is the left mode tree, it's going to come back up here and try the next one. That's what the selector does, right? However, in the sequence, both of these two must be true in order for this to succeed. So if the door is open and that's false, well, then this thing is false immediately and it goes back up to the selector, right? Whereas if the door was open, true, well, then this is so far true, I can go and try this one. This is the next node in the sequence, right? Notice again that each of the subtrees that is part of this particular node, you have more than one child, and it's not, or sorry, more than two children potentially, as it is not a binary tree, okay? So that's how it works. So if this is true, then we're here, so far it's true, and we come to here, and if we can move into the room, if something is blocking the room, let's say there's an obstacle, as an example, be in front of the door, then you know what, this is false, so then this becomes false, and then we go back up here, and then we try this one. That's how it works. Now let's move to the door. Okay, cool, I moved to the door, now open the door, right? So, again, it's kind of a weird example. It's not really complete, obviously, because, it doesn't take into account all contingencies for what's happening here. But this is the basic idea. So again, going back, selector is a circle with a question mark. A sequence is a rectangle with an arrow, and that denotes that you're going to do each of its children perform each of these children in sequence. Okay, that's what it's going to do. This is going to produce one of them. The first one that is the successful one. Okay. All right, so that is this one. Here's a more completed refactor tree of what we did before. So now you have a sequence. Okay, the sequence goes down to the selector. The selector basically says, remember, it's going to return true if all of its children return true, but there's only one child in the sequence. you can refactor it this way as well. So you're going to say, okay, is the door open? If this is true, right, then we return true. The door's open. And that kind of returns up to here. And because this returns true, then, well, this is true. The whole sequence is true. The door is open, right? How about this one, though? If the door is not open, then the sequence, the selector is going to choose the next one. And the selector's child is a sequence, right? So, okay, move to the door. And then if that's successful, then we're going to open the door. If it's not successful, well, the door is open, but we couldn't move to the door for some reason. So this whole thing returns false, right? Can't do either one. Well, then it kind of returns false, right? But we're going to try both until one of them is true. Okay, that's how the selector works. So a way of refactoring the same thing that we saw earlier. So the box with the arrow represents a sequence of events, right? So going back up to here, the box with the arrow says, I'm going to do this sequence. But in order for me to perform this sequence, think about what a sequence is. I'm going to have, let's say in here I have 2 tasks in the sequence, the open door task and the move into room task, right? In order for me to be completely successful with this sequence, this whole thing has to be successful, then both of these things are possible. I can move, I can open the door, the door is open, so that condition checks, and move into the room also checks in order for me to have this as true, right? But the selector, either one of these 2 cases can be true in order for the selector to run true. Does the arrow and direction matter? Well, no, but typically we start from the left to right. That's how the selector, the sequence works. It does determine the order. So the order that you have your children in, as an example, from left to right, are the ways that you're going to run the sequence. Okay, so let's move on. So now let's get into a behavior tree for a minimally acceptable enemy. Okay, so let's take a look at this one. And again, I love looking at these things because it gives you a sense of what's going to happen. Let's see. So again, at the top, we have a selector. That means either one of these 2 things can be true in order for this to be true, successful. All right. So we come here. Can I open the door? Let's suppose the door is locked, guys. Okay. So the door is locked. So can I open the door? And let's see how the enemy AI is going to function. So no. That means this is no. That means I come back to here. So now I don't even do this one, right? I don't do this one at all, right? Because we weren't able to come to I can't do this one, therefore this whole thing is false, right? Okay, so I'm now up here. I'm back to here. Okay, now I'm in the right subtree of this one, of the selector. Okay, cool, I have a sequence. I move to the door. Can I move to the door? Yes, I can. Check. I go back to here. Okay, and the second one, I run this piece, which is a selector again. Okay, cool. I'm going to try this one first, remember, and then I'm going to try this one to see if it's true. On this side, is the door locked? Yes, it is. Check mark. Okay, I move to the next part of the sequence, and I go here, open the door. Can I do this one? Yes, I can. I've opened the door. Then because this returns true, I don't even do this part. This part is not done because I return true here, right? If the door was locked, yes. Can I open the door? Right? Yes. Let's say I have a key. Then I go to here. All right. So now I've returned true here, and this is a sequence. I've done this one, and I've done this one. With now I got to do this one, which is move into room. Check. And so now because I've done these 3 things, and because one of my subtrees in my selector, right, is true, that means this whole thing is successful. Okay. Does that make sense? Let's try redoing this, right? And let's say that the door is open. Okay, let's try doing this, and the door is open now. So there is no lock on the door whatsoever. It's unlocked. Okay, and so we come to the door is open. Is the door open? Yes, it is. Well, we go in the sequence, and then we move into the room. We did both those 2 things. This checks out, and so this finishes right here. We don't even bother doing this one, right? Because we've already have a success. The first success is what makes sense for this one, right? So we don't have to do any of this. Okay. And the more complicated one is when you have to try all of them, right? So for example, the door is locked, but there's the key that you have, or you don't have a key to open it up, right? As an example. So you need to barge the door. So again, the door is locked and you don't have a key. All right. So door's open, no. So this fails. So this way we don't do this one. This whole thing fails. We go back to here. Can I move to the door? Can I move to the door? If there's some kind of obstacle preventing me, then this whole thing fails. The whole thing is a failure, all right? But let's suppose we can move to the door, right? We go here, and now we go to this part, okay? And then that takes us to this left subtree. Is the door locked? Yes, it's locked. Can I open the door? No, I cannot. This fails, right? So it comes up to here and tries this part, okay? So now I'm going to barge the door. Okay, I've barged open the door. I broke the door down. And then what I'm going to do is I open the door now. Cool. So this is good. This succeeds, which means this succeeds. Now I'm here. Now I move into the room. That succeeds, which means this succeeds, which means my whole thing is a success. Okay, that's how behavior trees work. Okay, they're a lot different than decision trees. They're not as easy to code, but they're more complex and they can include more complex task orientation. All right, that's the basics. Any questions around this so far? Because this is the basis of what we're going to be talking about in the next slides. Right? So how do we do it? How do we implement them? So again, they're made up of independent tasks. So each task doesn't depend on other tasks. And each task has its own little algorithm for implementation. Okay, that's the one thing to know what it is. All of them conform to a basic interface, right? Which means a basic structure, which allows them to call one another without knowing how they are implemented. So it's a black box. Each task doesn't know what the other task is going to do, but it knows how to call that task into being, right? Let's take a look at how this works. So here's a class task, and this is the kind of root task or the superclass task. And normally for this kind of thing, it's probably going to be an abstract superclass, right? And the only thing that each task returns is either true or false when we run that task, whatever that run task is. Again, here in this abstract, pure virtual class, if you will, the run function is not defined. We're not going to define the run function here, right? So what we do now is, what about if I have a class that has that is a kind of derived from the task class? For example, enemy near. Okay, enemy near returns a Boolean. We can say if the distance to the enemy is less than 10 units, then return true. So that's what this enemy near does. That's how you would run this task. All right. So here's another example of a sample task that could play an animation, right? So class play an animation, that's a task, right? The animation ID would be a number, whatever animation some kind of way to reference that animation. You might have a speed for how fast the animation is going to run. And then in your run task, or your run function, which is, again, all tasks have a run function because that's what we defined up here in the superclass, right? Then if my animation engine is ready, like in other words, I might have an animation engine in my framework, then let's play the animation with this animation ID, right, at a specific time, and then return true that the animation's been played when it's done, okay? Else, the animation engine's not ready to play. Somehow maybe it's already playing something, and therefore we are going to return false. We can't play this animation. It's going to fail, right, as an example. The whole task fails. Okay, so the run function is the thing that we're going to be checking. How about a selector? So a selector is a type of task too, because everything is a task, right? So here's the two things. So selector, remember, is the circle with a question mark on it, right? And a sequence is a rectangle with an arrow, right? So the selector is a type of task, but it has child tasks, an array of child tasks, one or more, right, of child tasks. So what we're going to do is we have a run function, and the run function is going to loop through each of the children, right? That's the selector. And if the run task is true, any one of them then returns true. So we're going to check for the first child that returns true, and we're going to return the whole thing as true. The whole task is going to return true for the run task, okay? The sequence does it differently. It also has an array of tasks, but what's going to happen is for every child in the children array of tasks, right? If that child is false, then the whole thing returns false. Otherwise, we're going to assume that that the whole thing is returning true because each child is returning true. So this is the way it would work. Okay, so again, a sequence is only going to return true if each of its children return true. So if each task that's related to its children are also true. Okay, that's how it works. All right, so what about performance? So we talked about performance of a decision tree, super fast. We talked about performance of a state machine, a little bit slower, somewhat more natural maybe, and more intuitive in some ways on how to put things together because you're dealing with states, okay? Combining, we saw also combining the two trees, the two types of systems, I mean, the decision tree combined with a state machine, not a bad idea because you have a hierarchical state machine that you can use as an example that decides whether you're in regular mode or, especially from an alarm condition perspective or in something else. So what we've asked you to do for assignment 3 and 4 as an example is we said, okay, cool. We said that assignment 3, you're going to have, this enemy that's running around. And in assignment 4, we said you need to use some kind of path node or some kind of node class, right? And what we're asking you to do is a bunch of sequences. We didn't tell you specifically what type of framework to use, but we're recommending decision trees. I don't think we said you have to use a decision tree or a state machine or whatever, right? We're leaving it up to you to decide what to do or a combination of. All right. So again, a tree is made up of just selector and sequence nodes and leaf tasks. So things that you're actually going to perform. And leaf tasks are conditions and actions. And that's O to the 1 in terms of performance, right? So linear. And memory is also O to the N in terms of, from a complexity perspective, big O notation, where N is the number of nodes in the tree. So the more nodes there are, the more memory you're going to have. It's linear again. Okay, so pretty straightforward. All right. So let's think about this. So far, all we've talked about is selectors and sequences. It's worth looking at some little variations that can make our AI more interesting and varied. And the implementations above run each of their children in a strict order, all right? And the order is defined in advance by the person defining the tree, and that's usually you, the programmer. And it's necessary because in our simple examples above, that we've been talking about, we have to check if the door is open before trying to move through it. That makes sense, right? Swapping that order would look really weird, right, as an example. And the same thing for selectors. There's no point trying to barge through a door if it's already open, because that is deterministic. You're going to do one thing at a time. Check to see if I have a lock. Do I have a key for the lock? Yes. Cool. Then I'm going to open it up. Is it already open? I don't even have to use the key because the door's already open. I can just walk through. Okay. So that's how it works. But in some cases, though, this can lead to predictable AI. And remember, we talked about this. Making AI deterministic, right, makes the game really boring. And if I can predict what the AI is going to do, then I can defeat the AI quite easily. And one of the things that we also talked about from a game design perspective is if we design AI to be deterministic and predictable, then the player is going to move out of being immersed in the game a lot of times, and it's going to kick them out of immersion. They're going to be like, wow, this AI is like really dumb, and I'm just going to just trick it because I know what it's going to do. It's going to jump to the right every single time I fire a bullet, right? So when it fires a bullet, I'm going to fire another one to the right because I know where it's going to go, right? And I can kill it that way, right? Or I know that it's going to do a predetermined pattern where after 1 second, it's going to pop its head out, as an example, to try and fire back at me behind cover. So I'm going to just wait there, right, as an example, sniper it, from a far enough position where I know it's going to pop its head out because that's what it's going to do. And I'm thinking something like Borderlands, where a lot of the enemies would just pop their head out, try and fire the bullet at you, while they're behind cover. As soon as they do that, I already have a beat on that location, and I'm going to beat the enemy, right? Christian says, that's the point of learning how to defeat a boss. Yes, it's true, but if the boss is complex enough, then that's okay. Do you know what I'm saying? If it's complex enough, if you watch the boss, if you're analyzing the boss, that's fine. And I'm thinking about Elden Ring. Sometimes, you have to die a couple times before you can learn what the boss does. If you're not doing a walkthrough or something like that, it's part of your experience, right? But if you're playing a game, as an example, and it's really predictable what the enemy's doing, like super predictable we're talking about here, then you don't have to work so hard to defeat the boss, right? Or defeat the enemy. So sometimes a lot of sequences, the actions don't have to be in a particular order. So we can do some randomization to switch that up. For example, if our room entering enemy decided to smoke the player out, they might need to get matches and gasoline, but it wouldn't matter in which order as long as both matches and gasoline were in place before they tried to start the fire, right? We don't know which one it is. I'm gathering resources, right? I'm gathering gasoline and matches in order for me to smoke you out. I'm going to put the house on fire, right, as an example, because you're inside of some kind of shack or something, and the enemy's trying to get you out, right? You know, so again, it's nice if it would be different every single time. If they get matches first and then the gasoline or whatever, right? So it's not the exact same order. So this kinds of constraints are called partial order constraints in the AI, right? That's what they are. And some parts may be strictly ordered, so I need to do something in a specific order, and some other parts can be in any order. So I may have the order doesn't really matter in this case, right? And to support this behavior, in our behavior tree, we use variations of selectors and sequences that can run their children in a random order. So I could have something like a random selector. So, you know, as an example, when instead of me running the children in a specific order, then I'm going to say, let's run my run task as an example, which is part of whatever. I have an array of children, and I'll say, okay, let's get a child that's random, right? So I'm going to choose a child at random. If that child task is true, then return true. Whichever one that random child is, that it returns true. So this randomness, though, has some issues. One of them is we might try to see the same child more than once, as an example. You know, so the same child will try it at the same time. And the other thing is it will never give up if all of its children repeatedly fail. So this is a problem, right? This could lead into an infinite loop, right? Because if I choose a random child, and then if that random child, as an example, in this particular algorithm, the way it's been written is if it fails, it could roll again. I'm just like rolling a die, right? Let's say, for example, I have 3 children, and I roll a D3. So I have a choice of 1, 2, or 3. And the first time I roll the dice, I get 1. So I return child 1, and child 1 fails. And then I roll again, and maybe I roll 1 again, and then that child 1 will also fail. And let's say I roll 2, and 2 fails, right? And then I roll again, I need to get 3. And let's say I roll again, and I roll 1 again. Then 1 fails again. And then I roll again, I roll 2. 2 fails again. And I never get to 3. It could end up being very frustrating for the player to watch that, right? So that's an issue. So a better approach would be to walk through all the children in some random order, right? And we can do this for either selectors or sequences using some kind of suitable random shuffling procedure, which we can implement like this. So first we shuffle the order, right? So we have a shuffled order for the children, and we run through that shuffled order as an example for the non-deterministic selector and the non-deterministic sequence. So you shuffle the, you have some kind of shuffling method that you use to shuffle the array of children so that you do it in whatever order you want. And all you're doing is that array is just going to be references or pointers to all the children that are inside the original children array, which is an array of tasks. All right, so that is non-deterministic, and here is your random shuffle, kind of mechanism, which allows us to, kind of create a new list. That's where you're going to return a new list or a new array, as an example, that you're returning from your original array. Okay, and that's the random shuffle that you're doing here. All right, so let's take a look at some of these. Right, so here are some example behaviors with partial ordering. Okay, so here is some partial ordering. So partial ordering means that, and whenever we have a randomness, we have some additional kind of syntax for this. Okay, so when we look at it, so anything that looks like this, that's ordered, task order, right? And anything that looks like this is random. Okay, random, ordered. Okay, so let's look at this and see how this works now. So let's do our little checks. So, okay, so can we enter the room? As an example, let's say we return true, and this whole thing returns true, and then we're done. Okay? How about this? Can I open the door? Right? So maybe I can't, get there, but let's say the open door sequence, the open door part of the selector. Maybe these two fail. I can't enter, I can't open the door, and I come to this part, and now this is random. I'm either going to choose, a 0 or a 1, right? Or, again, it really depends on what randomness you want. You can make them so they're not exactly equal chances. You know, the probability might be not 50%. Maybe you're going to make it, 30% of the time I barge the door, and the rest of the time, 70% of the time I do this sequence. Okay. It's really up to you how you set this up, and this creates the more of a complex brain for the AI. So let's suppose I rolled a 1, not a 0. 0 to 1 might be just like, again, maybe a 1 or a 2. So a 2-sided die, or, or it could be a 6-sided die with 1, 2, or 3 is barge the door. 4, 5, or 6 is, do this sequence. All right, so let's say we rolled 4, 5, or 6. Okay, cool. So now we must do this one, or this is in partial order. So I must do this one first. This one here must succeed. But now which one do I do first doesn't matter. So I'm going to start, and I'm going to say that let's get matches, right, as an example. So I'm going to get the matches here in my order. Now notice it says there is an arrow here, not a question mark. So that means I must do this one, both tasks, but it's going to be done in random order. Okay, so I'm going to get, let's say I roll, again, because I only have 2 choices. Let's say I roll a d6, 6-sided die, and 1, 2, 3 is get matches, 4, 5, 6 is get gasoline. Let's say this time I roll 1, 2, or 3. Then I start with this. I get my matches first. I come back up here. It's checked because this is a sequence, just random sequence. And I come down to here, and then I get gasoline. This is back to being checked, so I've checked both. I can get both. And now this is good so far. So far we're good, right? I douse the door. Can I do that? Yes, I can. And then after that, I ignite the door, and this smokes the player out. This succeeds. Either one or the other succeeds. I rolled this side. I didn't barge the door. I tried to smoke them out. This is the smoke them out sequence, right? And then because of this, even though these 2 failed, this one succeeds. Therefore, my whole attempt to do what I have to do completely works. So that is a little bit more complex behavior. And that's what behavior trees do. Behavior trees allow us to program or, kind of create more complex scenarios than decision trees or state machines as easily. Let's just put it that way. They're made for behavior as opposed to handle states or simple decisions. Yes, no. Do I have line of sight? Yes or no? Kind of thing. You can still use, behavior trees for the same thing, but it's just a different way of thinking. All right, so far we've talked about, different kinds of tasks, and we've met 3 kinds of behavior trees, and tasks in the behavior tree: conditions, actions, and some kind of composite, right, which gives a sequence and selectors, right? There's a 4th, which is pretty significant. It's called decorators, and the name decorator, what it does is it basically tells us we're modifying that selector or sequence node in a specific way, okay? So how does that, what kind of decorators can we have, right? So a decorator is a type of task that has a single child. That's one thing that's important. That's what about a decorator, right? And you can think of it like a composite task, only with a single child. So same kind of idea, right? And unlike the handful of composite tasks that we talked about before, right, there are many different types of useful decorators, and we're going to talk about some of them, okay? Another way of thinking about decorators is that they are sometimes called filters, some way of filtering or modifying the task, okay? So here is, limit, which is a type of decorator. All right, that's what we're saying. And limit gives a run limit. How often or how much are you going to run, as an example, that particular task, right? As an example, before you finish. Okay, that's what you're doing. All right, so it gives you kind of a limit to how many times you can run the task. So that's a decorator, right? A type of decorator. Until fail, this is a really good one as well. So you're going to keep trying the task until you fail. Okay, so that's what's going to happen as well. So here it extends decorator, and we're going to have a run task, and while it's true, right, we're going to say that we're going to run the child task until you can't run it anymore. A good example of until fail is maybe something like, I want to keep attacking you, and if until I fail, I'm going to keep doing it. And the only way I can fail attacking you is if you die, or if you kill me, or if I can't attack anymore because you've taken my weapon away, or something else. Until fail. So here's example behavior tree now with some decorators. Okay, and decorators have a different way of being drawn here as well. So again, we have at the very top a selector with two types of predetermined and ordered tasks. One of them is a sequence and the other one is another selector. Remember that the only way that this is going to work is if one of its children, either the sequence subtree or the selector subtree, is going to be true. Either one, as an example, is okay for the whole group of tasks to be true. All right, so let's take a look at the left subtree first. We're going to start with the left one instead because we're in deterministic order in this particular case. We're not doing random order. Then we're here at the top and we say that, okay, cool. So I'm here in a sequence. Let's start with him. Is the player visible? All right, okay. If it's no, if the player is not visible, then this whole part fails. So this whole part fails, right? And we go to the next step. The player is not visible. Okay, cool. So now I'm in a selector again. Okay, cool. I have a task that I'm going to go to, the sequence that I go through first. Is the player audible? Okay. And if the player is not audible, so this is false. Let's say these are false. I can't hear him and I can't see him, right? Those two things are the way it is. Then this thing fails, right? So this so far is a failure. But now, because the selector can do this, move is going to be something that is true because I can most likely always move, which means I return true and I go back to this. That's one way of looking at this, about this behavior tree. Let's try another possibility. Let's clear that up. And let's try the other way. Okay, the player is visible. Check mark. Cool. All right. I'm in my selector now. Until fail. Here's until fail. I go to this sequence. Right? Here's my sequence. And I go down to here. Are you conscious? Right? Am I conscious? Yes. Cool. I come here and I hit. Right? I come here. I pause. Come here. And then I try and hit again. Right? And then I come back to the until fail. This is true. Until fail. I come down here. Am I still conscious? I hit. And then I pause and I hit. Am I still conscious? I hit. I pause and I hit. And I keep doing this and forward until I'm not conscious anymore, which means this failed. And then I come up to, you know, and maybe it's not me that's conscious, it's the player, I think is what's happening here. So let's try that again. So the player is the player conscious? Yes. Okay. Keep getting them until the player is not conscious anymore. Okay. The player is not conscious. So that means this fails. And once this fails, this checks. Right? It failed. So this checked because one of these things failed. Cool. I come back to this sequence. I go down to here and restrain. Check. And because I've restrained the player, right, then this whole thing checks and then I'm done. Okay. And that's how this until fail stuff works. So that's a decorator. Decorator modifies the or changes the node underneath it, whether it's a sequence or if it's a selector itself. So with this is kind of a visual language that kind of gives us a lot of complex decisions that we can make, which is pretty cool, right? So in addition to filters, as an example, which is something that modify how we call our tasks, other decorators can be useful, and they modify the status code returned by the task. For example, an inverter node. If I get true, then I'm returning false. If I get false, then I'm returning true. So that's kind of the way it would work, an inverter node, right? And the base decorator task, which we haven't talked about right now, is just another task. That's what it is. So all decorators are just tasks, right, as an example. So that's how they've been all kind of inheriting from the base decorator, base task node, which means all decorators, since they're tasks, there's just tasks, they always have a run function, which is pretty cool. All right, so we can guard resources with decorators, right? So that's a way to do that, right? So to make sure that the resource is available before we run some action, we can do three things. Hard code the test and the behavior, bad. Create a condition task to perform the test and then use a sequence, or use a decorator to guard the resource. Let's use a decorator to guard the resource. So, so let's say we have a sequence, and is the animation engine available, right? And then we play the animation. That's the sequence. If it's not available, right, then we wouldn't play the sequence and this whole thing would fail. Okay? So really what we think about is they call that version of a decorator something called a semaphore, right? And semaphores are interesting, and this is something it's a mechanism in AI and also in computer science. That's what a semaphore is. There are mechanisms for ensuring that a limited resource is not oversubscribed, which is kind of cool, right? So what we want to do is we want to be able to make sure that I can acquire that resource. That's what the semaphore does. And basically when the code is finished doing what it's supposed to do, for example, it's finished doing its animation and the animation engine is free, then it's going to notify the semaphore that it can be released. So that's what it does, okay? So again, think about the class Semaphore as an object, right? Here we are. And we're going to acquire or lock that particular resource. And then we're also going to release, right? So either the resource is available or not. If we acquire, then we lock it. If we release it, we unlock the resource for being used. Okay, kind of an interesting way of doing things. So now semaphore guard extends decorator, decorator extends task. So semaphore guard is also a task. A semaphore guard has a semaphore, right, which is a type of way of locking and unlocking. It has the ability to lock and release, okay, as an example, or acquire and release is what they call it. And then what we can say is when we run our tasks, it's going to return true if if I can acquire the task, right? If I can acquire that thing that I'm looking for, that resource, right? Then the result is I'm going to run that child task, right? As an example. And then when the child task is done running, I'm going to release that resource and return the result where the result is true. Okay, so I'm going to keep running that resource, and when it's done running, then it's going to let me know and it's going to return true. Otherwise, I'm going to return false back out here to the semaphore guard. Great way of using a semaphore guard is you can combine it with a until it's true. So you keep waiting and waiting and waiting, and this is kind of a blocking sequence, if you will. It's not asynchronous. It has to run. As an example, maybe you have to wait for something to happen until you know and something else can happen next. And this is one way of doing that, which is kind of interesting. Okay, so I'm going to move on to something else. So one thing we can talk about is concurrency and timing. And concurrency is something that happens when we're running parallel tasks. Okay, so far we've managed to avoid the issue of running multiple tasks and behaviors at the same time. Decision trees are intended to run really quickly, you know, giving a result that can really be acted upon right away. State machines, long-running processes, but their state is explicit, so it's easy to run them for a short time each frame. Processing any transitions that are needed, right? Behavior trees, they're a little different. And sometimes we have to have actions in our behavior tree that takes time to complete, right? Almost like we're waiting for that event to trigger, right? We have an event that we're waiting for, so that time is done, and then when it's done, we're going to move on to the next thing, right? So example, moving to a door, playing a door opening animation, and barging through the locked door all take time to do, right? It's not something that's going to happen every frame or every other frame. It might take a series of frames or X number of seconds even to complete this whole task sequence, okay? So, so again, so far, the ones we've used are actions that complete instantly. Do I have line of sight? Instant completion. Is the door open? Instant completion. I can do that kind of stuff, right? So to improve this, we can assume that some sort of concurrency is available. The ability to do multiple bits of code running at the same time, or like we say, you know, where each behavior tree runs its own thread, okay, if you will. And that way, an action can take some seconds to carry out. The thread just sleeps while it's happening and wakes again to return true back when the above action is done, okay, as an example. And this would work, but typically, you know, we have only X number of threads typically to use, and adding additional threads for each character. Imagine you're using multiple processes for each character. That's completely unacceptable. The overhead for running that thing in a multiplayer scenario with a bunch of different enemies would be almost impossible. All right, so just going to move back just to check on YouTube if you have any questions. So we can have a pause task, right, that allows an autonomous character to wait a moment between actions to strike the player, as an example, or to pick up something or whatever. And that pause task is a type of task, right? So it's called wait, let's say. It has a duration. We can say a duration in milliseconds or a duration in frames. There's different ways of putting together that duration. And then it's going to perform the sleep task, whatever that is, right? It's going to wait for a bunch of times before, and when that sleep is complete, then it's going to return true, okay? So we can use it to time out a long-running task. If you really want to do that, we can limit a task number of events. There's a bunch of things to do when it comes to waiting, and it's kind of neat that you can do that. How about parallel tasks? Tasks that run, kind of, we start one task, and meanwhile, we'll go to the next task. We don't wait for one to complete before we start the other one, okay? So we can make use of a third composite task, and it's called parallel. And along with selector and sequence, it forms the backbone of almost all behavior trees, because we're running things in parallel. We're doing things at the same time or simultaneously, right? So one of the child task ends in failure. Parallel will terminate all of the other child threads that are still running, and just unilaterally terminating the task could cause problems. So the termination procedure is usually implemented as a request. So I want to stop the task. That's what it's doing. And then when the termination request triggers, it terminates all the other tasks. So here's a task that's changed where we have two things. I have a run task, which is going to return bool, run function, and a terminate function that doesn't have, it returns void. Okay. So those are the of the two functions that it might have now instead of just one. So it has run and then terminate. Okay. So basically what we can do is if parallel extends task, as an example, then I can have, here are all the running children. I have an array of tasks, all right? Here's an array of tasks. And then what I have is, kind of the result, whatever the upper end result is, right? And then I have my own run function for parallel. And then I start with the result that's null. So it doesn't have any kind of result at all. And then we might have some internal functions, defined locally to run this method, whatever else we want to do, right? And then what I do is I run child, and I start basically passing in the first child to run, whatever that child is, right? And then I add this new child to the running children array. So these are all the children that are running, right? And then what I'm saying is, let's run that particular child. Let's call the run task on that child, right? And then when it's completed, right, when it's returned finally, then the running children are minus equal to that child. We remove the child from the sequence when it's done running. And that kind of allows you to run each of the children in parallel, each of the children that are in the array. Okay, we're not waiting. We're going to keep on, we're going to call this function as an example that allow me to run each of the children if they're not already running. Whew, right? So parallel task running. I'm not going to go through the rest. Again, it's just there for concurrency. But this is what my concurrency might look like, okay? And notice that there is this one, all right? So this is a sequence, right? Or sorry, a selector that has multiple children. We're going to run a random child. That's what this does. So I'm either going to retreat or take cover, or I'm going to do this one. Notice that there are these three arrows. These three arrows mean I'm running a parallel. That's what a parallel is, 3 arrows. And I'm going to start off with this one. So this is going to be something that I can run. I can run this one or this one, and they're all going to run at the same time. I'm not going to wait for one to return true or false before I try and start the other one. So again, I have multiple soldiers here. Soldier 1, Soldier 2, and Soldier 3. They're all going to do their own things. I'm controlling it with my parallel task. So Soldier 1, do I have ammo? No. It returns false back up to here. So Soldier 1 failed, but it doesn't matter because I want to run all of them at the same time. Soldier 2 has ammo. Yes. Am I in cover? Yes. Okay, fine. Sniper attack. So that worked. Check. So I got a check mark from that one. And soldier 3, I have ammo. Soldier 3, do I have an exit route? No. So this one failed, right, as an example. So one of them passed. So which means this passes, which means this pass. As long as one of these tasks pass, then the whole task pass, which is kind of neat. But I run them in kind of in parallel order instead of a specific order, which is kind of neat from a timing perspective. Okay, I'm going to skip this piece because this is all about running parallel tasks. And this is a behavior tree version of the state machine, which is kind of neat as well, right? Which is that, remember that old state machine that we had from last week where we had a robot that would run around a station to try and find the trash? Okay, so we have a selector. The selector chooses one of these two things. It's going to start with this side because it's deterministic in this case. And then now this one is running two parallel tasks. Until fail and tidy trash. Okay, so it's going to run both of these two things. So I'm going to run until fail. Is the trash visible? Keep looking for trash. That's until fail. Okay, fine. The trash is not visible, right? So then if the trash is not visible, I failed, so check mark, right? Then meanwhile, I'm tidying the trash. Can I tidy trash up? There might be another sequence of stuff that I have here for tidying trash, okay? And then the same thing goes with this one. Until fail, I have an inverter. If the trash is visible, then return false, right, as an example. And it's going to kind of carry back up the line until we get to this point. So a very interesting way of using a kind of parallel tasks to do the same thing. Okay, so this is about intra-task behavior. So right now, as it stands, the tree shown would never run a return as long as the player didn't move out of position. The character would perform its actions, then stand around waiting for the until fail decorator to finish, which of course it won't do as long as the player stays put. Okay, and we could add an action at the end of the sequence where the character tells the player to head for the door, or we could add a task that returns false. Both of these would certainly terminate the parallel task, but it would terminate in failure, and any nodes above it in the tree would also know that it failed after completion or not. So there are some examples, some code of how we have something called an interrupter, and the interrupter extends the decorator. That's another type of decorator, where the interrupter can interrupt the task from running. And the reason why we want to have an interrupter is we're waiting for a bit of time, and you know what, where we keep on waiting for so long, there's nothing happening, and we've gone outside the wait period, and we want something for it to do, so we just interrupt that task. Okay, so I'm going to move on to some of the other things. So adding data to behavior trees is very interesting. So far, what we've done with them is we have actions. We're only performing actions. So our action might be a smoke out, which is I want to smoke you out of the room, right? And matches will fetch matches, gas, fetch gasoline. Those are kind of like tasks that are involved in the sequence. And then douse door, that's also a task, and then ignite. So those are the 4 tasks that are required in order for me to smoke you out, kind of thing, right? And that's what a subtree might look like if I was almost like a little subroutine if I want to smoke you out of the room, right? So again, here is the sequence. Is the enemy visible? Yes. Select an enemy, write that enemy. We want to kind of select that enemy. We're going to save that enemy, whatever that is. Cool. Next, let's select this one first. Either one of these could succeed in terms of as an example, in order for this node to succeed. Now this must succeed in order for me to do the engage enemy, right? So let's try this one first. So my sequence, right, is going to be high ground available. Yes. Then move to high ground. Now it doesn't really matter if I can't move to high ground. Here's something interesting, where I'm always succeeding anyway. This is going to be true no matter what. So if I don't do this high ground stuff, well, then I'm going to succeed anyway. And I'm going to engage the enemy when I'm not on high ground. I'm going to engage the enemy from where I am. Okay, so this is a way of doing that. So I can't fail. This task cannot fail. This is going to be either one or the other is true. Well, the other one is always true. Therefore, I'm going to do this one first. I'm going to try to do this, right? So this is what I'm going to try to do, which is kind of interesting, right? So again, another way of combining these sequences. So this is I'm going to try, right? And then this is going to always succeed either way, right? Because that's what always succeed does. If I can't do this, well, I'm only going to succeed here anyway, and then I can engage the enemy, right? So this is kind of interesting. Now, the only thing that has to happen is I have to be able to select an enemy, and I have to be able to engage that enemy, right? Now, when we say write and read from Blackboard, that's just a matter of saving the enemy, which enemy I'm selected in data, and then getting back to that enemy again. Because to think about this, the Blackboard would be something that is globally available to me, no matter which task I'm in. Okay. All right. So again, an interesting way of putting things together. And I think that behavior trees, although they're interesting for us, something that I've talked with Alex about a lot is implementing this with the time we have is always a challenge. And also understanding what each of these nodes are and how they work. Again, the way the UML diagram looks here might be also confusing. So what I've done for you is they've given you a couple of things to help you. One of them is a link to this really neat article. And again, it's a game developer article, which it talks about how some of these things would work, right? This is some really great stuff. It talks about the basics of how to use, how to use behavior trees. And it talks about that there are 3 statuses, as an example, that you might have from a workflow perspective, which is kind of interesting. Success, that's a status. Failure, and then what if I'm currently running, right? Because that can be something of a status as well. We talked about timing. Well, if I'm already running, wait till this thing is finished running. If I'm going to check your status, the status that it's in the top tree is running, or the root is running until I have success or failure, okay? And so when we think about this, composite, right, you have multiple things. You might have a decorator, and then you have some kind of leaf actions, all right, that are doing that are in here as well. Again, very interesting the way this article looks at behavior trees. I'm going to skip down to some of this. So a sequence, what it does, again, it goes through in sequence. So notice there's no diagram. There's no UML here. It's just a sequence. And it talks about what the sequence order first. We go from walk to the door if it's success. And then if we're in success state for walking to the door, the whole sequence is in running state. That's the way it works. So while I'm running the sequence and until I get failure, the sequence is in running, it's in running state. That's the status of the sequence, okay? So if I keep going there and I keep going from one thing to the other thing, at the end, the sequence is a success. It changes from running to success. If I couldn't go through the door for some reason, then the whole sequence would end in failure. So that's kind of a neat thing, right? And this is what this article talks about. It also talks about decorators and how they work. So example, the inverter node that we talked about before. I'm just going to zoom in here. So here's the sequence. Am I hungry? Check. Cool. Do I have food? Check. Yes. Here's an inverter, which is a decorator node. Are enemies around? No. Check. That means I can eat my food, right? If enemies around, yes, then this is a failure, which means the sequence is a failure because even though I'm hungry and I have food, there's enemies around, so I'm going to exit out of this whole sequence. That's the inverter node. All right, and that is the sequence. The selector is something else. It's going to return true if either one of them is working. So here's our sequence, walk through the door, and then we get to our selector, that circle again, right? Either one of these 3 things is okay, right? And I'm going to start with open the door. Can I open the door? No. Okay, back to this. I'm running, right? Back to the sequence. Now I have to do these 2 things in order. Unlock the door. Can I unlock the door? No. Okay, so those are 2, wrong. They're both fails. Now smash the door. Okay, I smashed the door. Either whether I smash the door, open the door, or unlock the door, I'm walking through the door in the next sequence. What if I can't smash the door because the door is too tough? Well, then this whole sequence fails. Whole sequence is failure. Otherwise, while I'm doing these other things, then the sequence, as an example, is in running status. Okay, that's how it works. So kind of a neat little article, and it talks about more complex scenarios about how it works for success and failure. Okay, and they have a little video here. They had a little video here before about how this thing would work, right? And they talks about leaf nodes and how they work and a bunch of other stuff. I think it's a really neat article, and I think it's worthwhile taking a read through if you're interested in behavior trees. Okay, so really good diagrams, and they go through the same kind of the stuff that we talked about in our PowerPoint, and quite a bit of detail. So I think it's neat, and it's a different perspective on the same things, the way they work compared to what I've talked about today in class. So that's one. The other resource that I've given you up online, which I think is also very good. I'm just going to go to that resource right now, and it's inside of the content for week 11. Let's pull that over here. Here's content for week 11. You can see that I also have, so that's that behavior trees article. There's also a GDC article that I've also included here, which is handling complexity in the Halo 2 AI, right? So it's another interesting article to read. Let's do that together, right? So let's do that. And I'm just going to briefly skim through it to show you what it's about. And it talks about, how they wanted to do AI with Halo 2 as an example, and how they did it was with a series of behavior nodes. So here's an example of the combat cycle, right? And the combat cycle, it's, for example, it's a directed graph, right? So if I'm starting in the search node, if you will, I have two options. I'm either idle, right, or I'm in combat. That's the search node. If I'm idle, then I can go to combat from idle, as an example. That's possible. If I go to combat, right, from combat I can go back to searching or back to idling, right? If I'm in combat and I'm losing, I can go to my self-preservation node, or I can leave. I can run away, right? Self-preservation might be including things like maybe, getting help or whatever while I'm in combat, running away temporarily, right, getting some health and going back to searching for my enemy again, come back to fight another day, right? So this is kind of the idea that they had, and this is an actual game that they used it for Halo 2 as an example. So this is the intent, and they talked about here much more of a complex, scenario, okay, where I have a kind of a directed graph, right, of different possible actions. Okay, that's what I have here. And each of these actions, here's the root actions of the graph, okay, the directed graph itself, right? Again, you can see that I have, different kinds of actions that I can take: idle, post-combat, engage, self-preservation, retreat, or vehicle. And each of these actions, as an example, has sub-actions. So for example, if I'm idle, I stand on guard, right? I come back to the root again, and then, in order for me to engage, I can try a grenade, I can try a charge, fight, search, where I'm searching for, cover or investigate, and so on. So kind of a very interesting way of the way they use this, kind of this graph, which is kind of neat, okay? So again, I think directed acyclic graphs like this are interesting in that they give us a kind of scenarios that we want to fit with our types of patterns or behavior, whether I'm using a decision tree, a state machine, or whether I'm using a behavior tree. I can fit these, these graphs and try and fit my data structure to kind of take care of these graphs. That's what I'm trying to do. So this is an interesting article. I would recommend reading through it. I think there's some really great things that they talk about here and how they handled it, and and how they handled this, the issue. And you can see that it has different kinds of behavior for different kinds of AI. All right, so infantry, drivers, and passengers, and there's different kinds of loadout and what they would do differently. So very interesting. So take a look at that. It's one for you to read, which helps you with understanding this kind of stuff altogether. So behavior trees. If I was going to draw one out, let's see if we can draw one out again now for our assignment 4. Let's see if we can do that. We did it already for, we did a state machine, and we also did a decision tree. But how does assignment 4 look, again, if I'm going to go back to this for behavior trees? Can I fit a behavior tree to this thing as well? Okay, so let's take a look at these two enemies, and let's try and think about a close combat enemy and how it would work. Okay, starts in a patrol action. Okay, so this is interesting. Let's just draw it out again, and I'm just going to use you know, kind of a program to draw with again, just like before. So let's think about this. So we're going to have the different actions inside here. The first action is the patrol action. So starts in this action. Okay, cool. This is patrol. And I'm going to use this as a task because everything in a behavior tree is a task. So there's the patrol task. And then what does it tell me to do? It says, okay, it continues this action until they have detected the player either by line of sight or if the player is within their detection radius. How do I write this, guys, now? I'm going to continue doing this action, right, until I have line of sight or not. Okay, so I'm going to do this, you know, as an example, and I'm going to see if I have line of sight. This could be a sequence. So this is one way I could write it, where I have a sequence. And the next one is, do I have line of sight? Check for line of sight, right? And this is the next task. I'm just going to write them here. So this is things we can do. So line of sight. Remember this one? And the other one is detection radius, right? Detection radius. We'll just call it radius. All right. And that is going to be the other one over here. Okay. It's going to make those as just little squares so we can see how this plots out. So we're going to do this. So there's our radius, line of sight, patrol, that's a task. What other things can we do, right? So move to line of sight and move to player action is the other one. So move to line of sight and move to player. We're just going to put them all down and we'll move them around afterwards. So here is a move to line of sight. Okay, that's an action that we're going to take. And the other one is move to line of sight and then move to player. To player, we'll put that down here somewhere. Move to player. Here's move to player action. We'll just make that a little bit smaller so it fits in there. There we go. Move to player. And the last one is close combat attack, right? So move to player and move to line of sight. That's also another one. We didn't do that one, so we'll do that one too. So that's also an action we can take. So move to line of sight. Or no, we did that one already. Move to line of sight, move to player, and then attack. Okay, so those are the ones. So one thing depends upon another thing. So, okay, let's start sequencing these things up in order for me to make this work. The other one we also have, if the player's health is 25%, then flee. So health less than 25%, right? That is a question, right? Or a condition. That can be a condition as well. And flee would be the action. All right, so we'll do another one of those and we'll say flee. So these are all the different nodes. So how would I position this, guys? What are your thoughts? Help me out with this. Let's do this together, this little exercise. All right, so I want you guys to understand how it will work. So first of all, would I start with a selector? Would I start with a sequence? What would I start with? What are your thoughts? How would you organize this thing? And we can have a sequence, a selector. Let's make it so that we have exactly what a selector would look like. So let's say we'll make it a circle. And inside the circle is going to be a question mark. All right, so that's the selector. And the sequence, we're just going to make one of those two, right? So if you're going to draw this out for yourself, and if this was an exercise, we would make this one and we would have an arrow. And I don't think I have an arrow available, so I'm just going to draw something that looks like this. There we go. That's a... Actually, you know what? I'll make it longer. Just because while you're thinking, I'll do that one. So I'll say this is an arrow like this. There we go. There's the arrow. And I don't know why I have the other arrow there, but let's undo that one. Let's just try that one again. Oh, that was weird. Okay, perfect. So I've got a selector, I've got a sequence. How would I draw this out? What do you think I should work with first? Well, remember what a selector does. A selector is any one of the actions are true, then it succeeds. Okay, as an example. So any one of the actions is true. So I want this thing to be successful. So let's start with a selector, right? And then maybe we do patrol. Patrol might be the leaf node, right? The patrol action, we didn't really talk about what patrol means, right? So when I'm patrolling, that patrol action might be another sequence that I'm taking, right? So where I'm, I patrol, I check for line of sight, and then I check to see if I'm in radius. These are things that I want to do, right? And again, and so patrolling means I move, right? I check for line of sight. If I don't have line of sight, okay, I check radius, which means I got to check all these three things, right? That's what I want to do. So I check for these things must be checked in order, line of sight and then radius, which means let's suppose that if I was going to take these two things together, right? And let's start with the bottom end, line of sight or radius, any one of those things is true. Okay. That means that this one I could position right here. Either one is true, then it returns true. Right? So that's what the first thing, that's definitely a kind of a connection that I can make. So either line of sight or radius is true, then this node returns true, right? If they're both false, then then I continue patrolling. Okay? So now how do I combine this situation together? Because either one of these is okay. I don't need either one is fine. I can go I check a line of sight. If it's not true, I check radius. If both these fail, this is failing, and then I continue patrolling. So what can I do here for this one? I can continue patrolling, and if this is false, if these two things are false, then this is true. This could be a decorator node, right? As an example that I move things off. Let's move them away. So just to give you a sense of this. This is one possibility, right? Where I could, let's just move this away. I could move, oops, undo. Let's just make them all together again. I want to select this one. And I could move these ones, right, to kind of sit there and say, and I'm just going to zoom out a little bit in a second, but this one would be part of an inverter node. So let's make an inverter node as well. We didn't really make that. So let's kind of make one with this one. So it's kind of, an inverter node might look like this. It's just it's a decorator, right? And that decorator would be, we'll call it just invert. And we'll use a not equals to kind of say that it's an inverter node or some kind of like symbol like this. That's a kind of an inverter node, all right? So whatever it is, it gets inverted, let's say. So we can put the inverter node, right, close to what we have over here. So we're going to grab this node here and put it over here. So this inverter node basically says if this returns false, then this returns true. Okay, it returns true. So that's what the inverse. We could do this. Okay, and I'm just trying to sequence it out with you to see what this is. So inverter node. And then the patrol action can be part of a sequence. Patrol, check for line of sight. Patrol, check for line of sight. And if this is false, then we can get out of this sequence, as an example, until fail. Until fail, right? That's something that we can do, all right? So let's do that as well. So this part, okay, I'm just going to move this around. So this would be like this, right? And this would be part of a sequence node, right? So again, we're going to just take this part. Let's move this a little bit closer, and we'll just move this, move these around a little bit so that we can see them. And I just want you to start thinking about, how I would do all this stuff. Let's lasso it instead. Makes sense to lasso this part. Oops. Let's do that again. Lasso. Wow. Yeah, that's what I meant to do. Okay, so then let's move this way down here, right, for example. And so this is the piece, and then we want some kind of sequence node. So again, we'll just take the sequence node here and we'll move it over here. So the sequence node says, this is going to work, right? And the sequence, I'm just going to make sure that I don't block them off. The sequence basically says, oops, make me look closer. It's basically going to work like this, where it's going to say that, okay, I want to run the sequence. I patrol. Can I patrol? Yes, I move. So check mark, goes back to, it's still running. Then I go over here, and this goes to the inverter node, which is a decorator. And it comes down to here, and I choose this one. Do I have line of sight? No. Do I have radius? No. Right, as an example. Then I come back up. And then because no, this is fail, which inverts this the result, which makes this true. So I keep going back to this, and this would keep going until fail, which means I'd have another inverter node. So let's say another node like this. We'll draw it like this, and this will be until fail. Okay, it's not going to be an inverter node, but this will be, kind of until fail. Okay, that's what this is going to be. So another decorator, but this one is an inverter, and this one's until fail. Right? We'll call it fail. Okay. So until fail, do this. Okay. And if it fails, then what? Well, I've detected the player, right? Well, now it depends on what happens. If I have line of sight, right, then what we want to do is, if I have line of sight, I want to mark it on the blackboard, right? That's what I want to do. I want to return true, but I want to mark that we have line of sight on, or detection radius, one of these two things, right? So it really depends on which one that I've I take to. And what I can do is I can check for these conditions again. One of these conditions is true, right? So I don't know which one yet. And I could theoretically mark this over here like this as another part. So I failed. And now I want to use this same sequence, the same idea, where I want to check if which one it is that I have, right? As an example. So if I have line of sight or radius, then I want to switch out of this until fail to come back out here again, right? So again, it's almost like I want to redo this piece again. Okay, but we want to refactor this tree. So hear me out when we get to that point. Okay, so I want to grab this one, because we're just thinking about it from one isolated, scenario, right? And the reason why I'm saying this is because I want you guys to consider, what we're kind of saying here. So let's just do one of these. So I want to grab this node again, right? And I want to copy it, and I want to paste it, but I want to paste it way up here. So I'm going to say basically, well, okay, fine. So it failed, right, until fail. And I'm going to start with this part, right? So I'm going to put this one over here, another selector, right? Let's see if this works. So let's put this selector over here. Oops. I want to, let's make sure actually that we're doing one of those. And I want to do that same selector sequence here, where I'm there. And move that over here, so on top of this one. Okay. So I'm saying, okay, so I start with this one. If it fails, try this one. Okay, so this failed, which means if it failed, the only way that this could fail, as an example, is if I have either line of sight or radius. Now I check. Okay, so this failed. That means I have line of sight or radius. Let's check. Do I have line of sight? If I have line of sight, then move to the player, right? I don't think there's in my document if I say that I'm close or not. There's nothing that says, it says if the player in the detection radius and not in line of sight. If I'm in line of sight, perform move to player action, right? It doesn't say if I'm close enough. Oh, there is. It says with close combat distance is another condition. And that is if I'm in close combat distance or not. So that is another condition. So if I have line of sight and am I in within close combat distance? This is something that I can put in there. So close combat distance, right? So again, I'm just showing you how complex it can be to program. right? Because we're trying to figure out a way of making the action work over and over again using a behavior tree, as opposed to using this. And we're going to have to refactor this tree in a bit as well, if you think about it. Now, again, I'm running out of time, so I don't want to, kind of take it out. If I don't have close combat distance, what does this mean? So I'm in line of sight, but I don't have close combat distance, right? I'm going to check that next. So it's like, it's going to check if this is true, right? Then the only thing is that this one is going to be in a sequence, right? So I could run, instead of doing this, I could say if I have line of sight or I have radius, then run a sequence. If I'm in close combat distance, then attack, all right, as an example. So that could be a sequence that I have. So that sequence selector would go over here again. I just don't have time to put it in here. And where I do an attack after I'm in close combat distance. Okay, if I'm in radius, am I in close combat distance? Again, I can do that same check. Then I can do an attack, right, as an example. But I'm in radius, but I can't see the player, which means close combat distance doesn't make sense. Which means move to line of sight is something that I got to do here. Move to line of sight is something that I want to do. And then I would check again. Do I have line of sight? Go back to here and check to see if I have line of sight, right? And that's a way of trying to start sequencing how this thing works. Again, I've run out of time, but you can see how much more complex it would be to set up. At the end, though, one great thing about using a behavior tree as opposed to a decision tree, and I couldn't finish on time, is the way that this would work is, you would have potentially a lot more complex actions, and you can build in some additional options compared to how a decision tree or state machine might work. All right. All right, so that's kind of the start of how we would order things for a close combat attack. Questions before we move on? Again, I just run out of time. I don't want to keep you beyond the time. That's why otherwise I would continue. So again, I think, we've covered a few different ways, few different decision-making patterns that we have so far in this semester. We've covered, like we said before, we've covered decision trees, state machines, and now behavior trees. Behavior trees are definitely the more complex way of doing things, but they can also lead to a much more complex set of actions. That's what I want to leave you with today. Last thing to note is for what we're doing this week from a lab perspective. So the lab is broken into several parts. This is part one. We're going to actually build a tree node class. We're building a condition class and an action class. Each of these kinds of classes are going to be ways of us constructing a decision tree. We're going to have the left subtree as well as the right subtree that we're going to use. The left subtree, again, we're making a binary tree, right? So there's going to be and we're going to try and make it as balanced as possible, just like I drew for you guys last week, right? And we're going to construct this AI brain with the condition and actions in place. So some kind of, these are kind of like super classes that we're going to create. And then starting next week, which is kind of interesting, we're going to test out a couple of conditions, and actions this week. But starting next week is where we actually start building the different actions. Notice that these are actions, and these actions are going to derive from the action class that we're going to make this week. Okay, so kind of an interesting way of doing things. The first action we're going to make this week is the patrol action, right? So it's going to do the patrol action depending on the condition. When it has line of sight, or when it has, if it has a sensing radius, it's going to stop patrolling. That's what it's going to do. Okay. And you can see that we're going to continue to help you build your decision tree as we go forward. Can you use this to build a state machine? Absolutely. You can use actions because a state machine also has a group of actions that it's going to perform. Can I use these actions to do a behavior tree? Yes, I can. I can plug in these actions as the different tasks that are going to be used as an example, as opposed to just, to just doing the tree itself. Okay. So there's like different things. Can I combine, decision trees and state machines and behavior trees? Absolutely. I can do it as complex as I want. And I can make for very complex behavior patterns. for my enemies. All right, any questions around this before we go for the day? So for the lab this week, again, we're going to be focusing on building our tree node class. Okay. Guys, I'm going to stick around if there's any questions around the assignment or labs or anything else that's come up. Otherwise, that's it for today. And see you guys Thursday.